Yep.
Okay, great. So thanks for the intro. My name's Erica. I haven't done a lot of my own original research in the Arctic. That's why Manuel is going to take over for the second half. But I'm just going to give a really brief overview of why sound is important anywhere in the ocean, really, and how it's a little bit unique up in the Arctic. So why do we care about sound in the ocean? Well, sound travels about 5 times faster in water than it does in air, and most of the ocean is dark. So if you're an animal that lives in the ocean, it makes a lot of sense to communicate using acoustics rather than maybe visual communication. So many marine animals are capable of perceiving sound, and many marine animals also produce sound to communicate. So lots of naturally occurring types of sounds in the ocean, like the sounds of wind and waves breaking on the surface, ice breaking, rain, storms, earthquakes, you name it. There's a whole lot of natural noise in the ocean. Then from biological sources, some of the reasons that animals make sound, basically the same functions for animals on land. So a lot of animals call out to find mates or make sound to defend territory. Some animals use sound for foraging, and some use it to perceive sound for navigation purposes. So these are sort of the natural sounds you would expect to encounter in any given ocean. And then, of course, in some parts of the ocean, we also have a lot of anthropogenic sources. This can range from vessel traffic to pile driving, seismic air guns, and sonars. So the combination here of these abiotic, biological, and anthropogenic sources, all of these things together comprise what we call the soundscape. And the soundscape is something that's really different across space and time, which makes it challenging, but also very interesting to study marine soundscapes. Anytime you put a hydrophone in the water, you never quite know what you're going to find, and it sometimes can be really clearly linked to weather events and things. Sometimes you find things you never knew you were going to hear, like some new cool animal sound. So to me, it's a very exciting field, but also very complex now with the addition of anthropogenic sources. So that's sort of like why we care about sound in the ocean. This is a figure that is a bit busy, but it kind of walks through looking at what some of these sounds might look like. So for example, if you're a right whale here, you might be producing sound to communicate with another individual, perhaps way over on this right side over here. You might be encountering natural sounds of fish in the environment, and then some of these anthropogenic sources as well, like the cargo ship and the submarine down here. So this is just a graphic. It was produced by National Geographic, and it's kind of cool to illustrate the world of a marine organism perceiving its environment through sound. So how do we actually measure and visualize sounds? This is important as a preamble to Manolo's talk, because this is probably one of the more confusing elements of marine acoustics. So basically, what sound really is or the way we measure sound is pressure changes over time. So usually when you make an acoustic recording, you will get your audio file, and you can spit out a couple of things. One of the things would be up top here, this blue figure, which we call the waveform, which is essentially just a squiggly line over time on the horizontal axis. And the measurements here, this one happens to be a relative scale, but this is essentially loudness. So it's showing loudness or perceived pressure over time. Then on the bottom, we have what we call a spectrogram. So this top is basically a squiggly line, but it's a series of a number of squiggly lines, and each of them have different wavelengths or different frequencies. So we generally care about the frequency of sound because that dictates what kind of animals can perceive it. So frequency is basically a measure of pitch when we think about perception. So on the spectrogram here, what you're looking at on the vertical axis is frequency. So low pitch down here, high pitch up here, and then you have the same time axis going across the horizontal. And the darker the color here, the louder the sound you're perceiving. So you can really think of a spectrogram like a musical score where you would read music notes across time. Now, what's also interesting from this type of measurement is to look at the spectrum. Now, the spectrum of the sound is basically a sliver of this spectrogram. So if you were to just take one little time interval here and then you rotate it and plot it on the horizontal axis, that's what the spectrum is. So you essentially have the loudness of the sound on the vertical, and then you have the pitch of the sound on the horizontal. So this is just like to orient you to how we measure sounds, and then the measurements, as I just explained, we have amplitude or loudness, frequency, and then the frequency composition. So how loud it is at each frequency. That's what the spectrogram shows. Okay, So I wanted to play an example. We'll see if the audio comes through, but this is an example of a bowhead whale call, and it's the same spectrogram I showed in the previous. Now the bowhead whale sounds are these low frequency grunts here, and then in the background you can also hear some bearded seals making sound as well. Let's see if this works. Nope. Okay, bummer. I'll try it up here. Yeah, okay, sorry. That's too bad. Well, you can all go to the Macaulay Library hosted at Cornell and find the bowhead whale sound and listen to it. Anyway, all right, moving on. So when we think about sound or noise in the ocean, one classic way to visualize it is what we call the Wenz curves, where essentially you're looking at a bunch of different spectra. So just as I walked you through before, you have frequency on the horizontal axis. This is in a logarithmic scale. And then you have essentially amplitude in the y-axis. And so all of these little lines here on the bottom right correspond to sea state. So, you know, the more windy it is, the more waves you're going to have breaking on the surface, the louder it's going to be. Then if you have a rain event, you might have some elevated sound levels up here in the higher frequencies. And then you can see that earthquakes are down really in the low frequencies. So this is sort of a generalized description of what we would expect from any given place in the ocean. But like I said before, it's highly variable across space and time, and especially with weather changing, it means the soundscape is going to be really different. Now, when we think about ice, so this is sort of a rough ballpark of where the sounds of ice breaking would fall in, and Manolo is going to show a couple of actual measured spectra from ice measurements, which is great. So this is just, again, paving the way for that. Then ice breaking ships may be further up here, so they're definitely louder, but they're lower in frequency content. And then another thing to note, not shown here, is that, as I just explained with the sea state thing, now if the sea state is really rough, you're going to have higher noise, but if there's actually kind of like no sea state, because the whole surface is covered by ice, it's actually going to be a lot quieter. So in the Arctic Ocean, when ice is completely covering, you're going to have lower ambient noise levels. Okay, and so one of the reasons here, this is when we think about propagation in the ocean, we often draw these little diagrams showing the sound rays. Essentially, imagine it like a sound wave bouncing off of different surfaces it encounters. On the left, we have a sound speed profile. So you would have the speed of sound is across the vertical axis and depth across, speed of sound across horizontal, depth across the vertical. And so when you have like a really clear, what's the name of the, when you have a point on a graph? Oh. Well, yeah, a thermocline. Inflection. Yeah, an inflection point, thank you. Like this with a clear thermocline, what happens is that the sound waves can actually bounce off of that thermocline. And that's a whole other conversation, but it relates to the fact that temperature and salinity and depth all influence the speed of sound. But again, a conversation for another day. I'm not trying to get that technical. But essentially what happens is you have the sound waves refracting upward, and then they're also bouncing off the surface of the ice. So this makes for a lot of interactions between the sound waves and the ice surface itself, which means it can be a rather complex sound field. Now, it also depends on the frequency content of the sound. So in these little ray diagrams, you're not necessarily discerning by frequency, but because the wavelength of a sound really influences a lot of things about its propagation, you always have to consider frequency. So in the bottom figure here, we're looking at transmission loss. So that's the amount, you can think of it like the amount of amplitude or pressure that's lost as it travels through a given distance. So distance is here on the horizontal axis, also in a logarithmic scale, or you can look at this in miles across the top, it's kilometers on the bottom. Each of these lines is a frequency. So you can see that the lower frequencies like 20 hertz, 40 hertz, 60 hertz, those tend to have lower loss in these ice conditions. And then the higher frequencies tend to have higher loss. So what this means is that in the Arctic, you have the ability to trap low frequency sounds, and the higher frequencies, they could be transmitted, but they're also interacting with that surface of the ice up here. So they're not very well transmitted either. So then this is looking at the Wenz curves again here with a couple of different scenarios. So starting at the bottom with the yellow line here, this would be an example of what kind of sounds you might encounter. This is with the idea of additional boat traffic being added in, but in really shallow water, low frequencies don't tend to travel very well anyway. So you're going to generally have lower sound levels associated with vessel traffic in that condition. And you can see the orange is slightly higher.
We're getting a bit of background noise, so please mute yourself if you are not.
Thanks. Okay, and then so let's see, in deeper water, with ice cover, you would still have higher noise levels due to the vessels because you don't have that low frequency cutoff with the shallow water condition. Now it's deeper water. However, when there's ice covering, these higher frequencies are not going to come through as much. So if you compare in your mind the green to the red, this is what the kind of difference you might see in deeper waters off the Arctic with ice cover versus without ice cover. So really the takeaway here is that in summertime conditions or time with less ice cover, that the vessel traffic would have a higher impact on the animals because it would transmit further than in the ice covered conditions in the winter. So why are we even talking about vessel traffic? Well, that's because it's on the rise up in this area of the world. This figure shows us the ice concentration in the solid blue bars and then a general trend of declining ice cover over time. And concurrent with that, you can see this gradual increase in vessel traffic. So as these waters are warming and there's less and less ice cover, there's more and more vessel traffic. So this is definitely something to be considering when we're thinking about the acoustic environment up in these areas. And then final slide to end with here, just zooming out for a minute, this is a snapshot of data that I recorded many years ago. This is not in the Arctic. It's actually really close to Long Beach, California, which is one of the busiest ports in North America. And this is essentially a 7-day snapshot of what the acoustic environment looks like. And I should say that even though it's not labeled, the axis on the vertical here of each of these is 1 kilohertz, and then along the horizontal, that's 24 hours. So what I want you to notice here is just the presence of vertical lines. And when you zoom out to a whole day in a given place and you look at vessels passing, they basically appear like these vertical lines. If you were to zoom in, you can actually see the vessel approaching and then leaving, which is kind of cool. But point is, there's a lot of vertical lines, and especially during the daytime when all the boats are coming through. And then these big red ones, presumably are big tanker ships that are coming in or just hanging out in that area as they're waiting to come into port. So it's a noisy place out there in certain parts of the world, definitely near Long Beach. Hopefully this isn't the way of the future up in the Arctic, but it's just something to think about. So I think that's it for me. Yep, that's my last slide. I think, are we going to hold questions for after Manolo?
Since you have to leave kind of soon, let's have 1 or 2 questions right now. Are there any questions for Erica? I have one. Maybe for Erica or Manuel or Stan. You just mentioned how sea ice can affect different frequencies. How does the presence of sea ice versus no sea ice affect directionality? Do the sound waves curve? Do they still go straight with sea ice?
In directionally, the sound waves have unless they run into an ocean front or a current or a different body of water, you kind of, in the horizontal, you normally think about things as being, the simplest solution is that our approximation is to think that it doesn't change enough to make a difference, unless you run into a severe thing like a front or an eddy or something. Okay. So they'll continue straight in that plane, in that azimuthal plane. Obviously, in the vertical plane, the sound is varying based on the sound, the sound speed profile that's there. So generally, because the ice is going to be directional, suppose you have a ship that's going by an ice field, the sound that's going on the south side of that, away from the ice, is going to propagate differently than the sound going under the ice. So you will have a distortion of the field with with the ice dampening the sound field, closing it in a little closer and making it reduce more rapidly. But again, there's probably no animals in that water.
Sure,
because there's ice there. So
yeah, it's an idealized situation. Thank you, Stan. Let's go to, is there any other question for Erica or Stan? Let's go to Manuel's presentation then. Manuel, you can get control by clicking on share screen at the bottom and center of your screen.
Can you hear me well?
You have to stop sharing your screen first, I believe.
Yeah, I cannot share until, Erica, you should stop sharing yours, see if it works. Okay, let's see if I can do it now. Yeah, share screen, is it working? And can you see the presentation there?
Yes.
Okay. Okay. And can you hear me well?
Yep.
Good. Okay, so I should go ahead, see if I can find my, okay, so, well, first of all, thank you for having us presenting today. It's great to be able to participate in this group. And so what I'm going to show here is just some of the work we are doing. Catherine Berchuk in our lab, she's leading all the acoustic program where we have a big number of moorings in the Arctic, and she's been able to maintain those moorings for over a decade now. So we have a very big database that's been mainly focused, it's been for marine mammal detections, ice noise, ship noise, and ergon noise. And so what we're trying to do now is incorporating this new approach, which is looking into the soundscape analysis, or kind of trying to describe the acoustic environment and which are the contributors to this acoustic environment. And we're just starting with this project. So what I'm showing today is just the methods we came up together to be able to process all this vast amount of data. And so before we can talk about how the soundscape is changing, we need to get a sense of what are the contributors to sound in the Arctic. So the first step is to characterize who is doing sound and when and where and what type of sound. So that's what I'm going to present here somehow. So the lab, as I mentioned, Catherine has been maintaining over 20 moorings in the Arctic, from the Aleutian Islands down in the Bering Sea all the way up to the Beaufort Sea close to Canada. So you can see those dots in this map. And some of these moorings are only acoustic recorders, which are the green triangles, but others have also physical and oceanographical biological sampling instruments in them. So it's a line of instruments in the mooring, including one recorder. And so I'm going to present data from site WT1, which is, oops, sorry, wrong site. This mooring up there, which is basically off the town of Wainwright. And we picked that mooring as a location to test our methods because it's an area that has a good representative coverage of ice in winter, also has many marine mammals passing through or staying in the area. And there is also anthropogenic influence. There is the Chakchi oil and gas lease areas, which are not far away. And also Wainwright itself, the town, is commonly used as a crew hub for several industries. So it's a good indicator for human disturbance. And that will be some of that I will show you. I wanted to show also this other map, which, as you can see, is the same moorings we are working with, but also all the gray dots are all the moorings that have been deployed over the past decade, more or less, from industry or other scientific institutions. And as you can see, there's a vast amount of material available, so we can look into that data for soundscape analysis or other type of studies in looking for trends and noise. So just wanted to let you know that our moorings are probably the wider and longer term data set available for the Arctic, but there's plenty of other recorders that have been deployed over the years. And so if there's more funding, there's definitely more things we could look into. So the next slide is showing you basically the steps for our analysis. Oh, didn't go. Yeah, there we go. So it's the analysis basically starts with what Catherine's team has been working over these past years, which is looking into the recordings and manually scanning through those to find what acoustic events are happening. So we're using a MATLAB script that was developed by Catherine, which usually helps the people analyzing the data to scroll through spectrograms and annotate all the occurrence of the 12 different types of acoustic events. Basically, you can see the right panel there shows the different species, as well as ice noise, vessel noise, ergon noise, and some identified categories that we can later revise. So the left panel is showing you, as Erica did a very good presentation showing you this spectrogram, and basically each of these green and blue blocks are 45 seconds of data or sound that the analyst has to go through and basically manually pick what is being detected in those particular periods of time. And so Catherine has been really training and coaching a group of analysts, because this is a tedious and long-term process to go through all these recordings by hand, but is basically the only way to really complete a detailed index of acoustic events that are happening in the recordings. That is basically a base for a lot of really interesting studies that we can do using that information. And so, for example, what I'm showing right now is a plot that is created with that type of analysis. So it's showing you the seasonal occurrence by sound type. So you see in this case, it's bird seals. And so you can see each of the vertical black bars is corresponding to the amount of presence of bird seal calls within the day, from 0 to 100%. And that's based on the recordings that are made on 80 minutes every 5 hours. So if you have a day where all your 80 minutes have bird seals, then you have 100% in that day. And so you can see how bird seals increase their calling activity by December, and then they reach a maximum of about 100% almost daily from April all the way to basically the end of July, when they basically stop calling. So the panel also includes the ice concentration in that blue line you can see there. Basically, that's based on satellite imagery. And so what we do is we look at the ice concentration over a radius of 15 nautical miles around the mooring location, and that gives a sense of how much coverage is there. So you can see how the ice concentration starts to be happening in November, and then it's basically maximized through the winter, and then by the end of June, early July, it starts to melt, and the concentration decreases until there is no more ice by the end of July or early August. So now I'm showing you basically a summary of all the different things that were detected in this mooring. So you can see that we had bowhead whales, walruses, pinnipeds of different species, and vessel noise, better seals, belugas, and ice noise. And so those figures are showing you the distribution over time, as well as the concentration or the amount of detections per day. And so you can see the ice too. The ice line is the same in each plot, because basically the same mooring. But basically what we can clearly see is that we have an open water season, which is what I'm showing there in red, and then an ice season, which is the blue section. And again, that's based on 50% coverage. So as soon as we exceed the 50%, then it becomes winter or ice season for us for our analysis. And so the main contributors for the ice season, which is the blue section you can see, is mainly better seals, bowhead whales, and during the spring migration, also we have some belugas that are, as bowheads are migratory, so they pass through the area, and then we get those detections in spring and fall. Or if you follow this figure, fall is November, December, and then what else do I need to say here? So vessel noise, you can clearly see, so it's happening mainly in the open water season, but it's also partially overlapped with ice forming period. So the beginning of the ice season, there is some vessel noise too there, and we'll see some more details about that on the next slides. And regarding ice noise, obviously that's only happening during the winter, so you can see how ice noise presence is happening, from November all the way to April, May, when the ice starts melting. So this next screen, what it's showing you is basically what we call a long-term spectrograph. Long-term spectrum average. Basically, is showing a full year of data in this case, and you see the time scale from September of 2013, I believe it was. Sorry, September 2012 to August 2013. And so it includes all the sound files with marine mammal detections, but no ice or anthropogenic noise. And I picked this particular LTSA because I think it's easier for you to see or to highlight the seasonality. If I use a long-term spectrograph with all the different noise sources, including ship and ice, it will be a much more busy plot. So I think this one is really clean, showing how the open water season is way louder by nature from wave action and basically waves generated by wind, as well as rain noise, than during winter, when you have a sheet of ice that is basically decoupling the water from the atmosphere, so we have no wind noise or any precipitation in the recording. So the bright blue region from September all the way to November, that's when there's no ice, and so we have all the waves and rain. And then in November, you see it's darker blue, so there's less noise, which means that the ice is basically making the area quieter. And so what we could do, if I could zoom into that, you could see that bowhead whales are dominating the open water season. So all that vertical light blue and red dots, those could be, you know, windstorms, but also it's also part of the Bowhead vocalizations that are happening in those days. Remember, those are slices of 1 hour. So what we do is we average the sound in 1 hour, and then we generate a slice corresponding to the average of that hour. So everything is really compressed in an hour there, and we have a full year, so you have plenty of slices. So the clearer slices correspond to days where there is more noise, and because we know there is bowheads in that area dominating, most of that energy is probably coming from bowhead whales and wave action. And then British seals are the main dominant contributor in winter, and it's not easy to see, but it's at the lower frequencies. You see where it says 11. Oh, actually, I can probably use my cursor. You can see my cursor, right? And so if you see my cursor there, that lighter blue stuff that is shown in that section of the spectrogram, that's mainly British seal sounds. And then we have some belugas that you can see it here that are higher in frequency, and they're happening for a few days in wide frequency all the way up there, and then other different sources of sound. So you can clearly see in this year of data how many different things are happening and how seasonal they are. So an important point here is it's important that we break our data sets into two periods, the ice and the upper water season, because as you can see, the natural background noise is very different in both seasons. So in order to describe the contributors of sound in the Arctic, you need to make sure that you are separating these two seasons. So this next slide is showing you basically one of our the first step in the analysis, basically. So what we do is we obtain a series of metrics based on the presence and absence of each contributor. So the natural background noise per season, so open water or ice, is characterized by using all the files that do not contain any visible contributor other than the waves or rain. So there is no whales, no ship, no air guns. So those files are the ones we use to generate these figures. And so the upper panel is showing you the spectral probability density for the open water season. So that is a spectrum, as Rika mentioned, that's the distribution of energy across frequencies. So the spectrum for each hour of data for all the hours where there is nothing else than wave and no ice and no vessels and no animals, and they're all overimposed, creating these density plots. So you can see that when those spectra overlap, we get bright blues, yellows, or even red colors. And when there is very few spectra, it's mainly blues. So it's showing you the distribution of the spectrum over all these thousands of hours corresponding to the upper water season. And so then we calculate the percentile spectra over this data. The percentile is basically a line that represents the 25% or 50% or 75% of the sound level for that particular frequency. So if you focus on the bright green line, let's see if I can use my cursor again. So you see the green line is the 50th percentile, which corresponds to the median, and it goes somewhere here. You can follow that bright green line there. So for example, if we stop here at 1,600 hertz, the level of noise would correspond to something close to 70 dB. So that's what is indicating that line. So the 50th percentile is showing us that 50% of the time at that frequency, back here, 1,600 hertz, we had about 70 dB levels of sound. So the 50th percentile is a very good summary or synthetic way to show the variability and levels of noise of this particular season, which is in this case the open water season. So we do the same for the ice season, where we have these probability density plots of all these spectrums, and then we have all these percentiles calculated. This would be the 50 percentile, the green one. So you see it's way lower compared to the open water. The open water is louder, and the winter is quieter. So the line is a bit down in lower dB levels. And so we could do this for open water season or ice season. Remember, this is data without any contributor, without seals, whales, sheep, so it's just the background noise. Or we can do the same for the different contributors. In this case, it's British seals. So you can see there's less spectra because there's less hours with British seal detections, and then we calculate those percentiles. And those are basically this is the main metric we are going to export from all the different selections of files from different moorings and different years. And if we, let me go to the next slide. If basically we extract that 50th percentile, what you have right now there is two lines. It is the median, so the 50 percentile for the ice season or the open water season. So that's just background noise. Again, you can see how the open season is way louder, is higher in dBs than the ice season. So it's a very good way to see differences in the sound levels across frequencies, basically. And so for this particular location, WT1 between 2012 and 13, clearly shows how the background noise is higher in the open water season than the ice season. So it's just one more example to show you how we can compare levels of noise in between different seasons. And see if I can go to the next slide. So now I'm showing you vessel noise. So what we did is, as before, we only pick those files that have vessel noise and nothing else. So if there is vessel noise but better seals, we exclude that file. We only use the ones with purely vessel noise in them. And then we run the analysis I showed you previously, and we extract the 50th percentile, which is what you see right now. So you have one curve for vessel noise during the ice season and one for vessels during the open water season. And you can see clearly that they're not very different in noise levels in the dB values, but you can see that the low frequencies are much louder during the ice season, and shipping happened only in the early, during the ice formation, so the November, December. Then when there was thick ice, there was no longer vessels passing in that area. But the level of noise generated by those vessels were quite higher than during the open water season. And there is probably different reasons for that, but I'll wait for the next slides to talk about it. See if I can go to the next. There we go. So now I'm showing again the same thing, vessel. So the orange line is the same one you saw before for ice season and open season, but then I am overlapping that curve with a 25th, 50th, and 70th percentile of background noise. So again, these lines are only the background noise where nothing else was happening. So those three lines represent the natural ambient noise variability in those locations, both in the ice season or open water season, and then we have the ship noise on top of that. So you can see that clearly there's quite a bit of a difference in how ship overlaps with those figures, with curves for the ambient noise. So basically, the median vessel noise exceeds the three blue curves in the, I'm talking about ice season now, the left panel. Let me see here. So you see the curve is crossing over the three blue lines. So it's louder than even the 70th percentile of ambient noise. So on very loud days when there is, let's say, a lot of wind or a lot of noise, a lot of noise naturally happening, vessel noise is even louder than that, at least for these lower frequencies, up to 1 kilohertz, about 1,000 hertz right there. And then the vessel noise is going down to the 50th percentile, about 3 kilohertz, and then it stays more or less on that level at higher frequencies. So we can look at how the vessel noise relates to the background noise and how much of a contribution is generated into that particular season, the ice season, in that particular location. In the open season, again, you see the vessel curve is always within 25th and 50th percentile of the background noise, so it's way quieter compared to winter, and in part that's because the ambient noise is higher. So we have an elevated ambient noise, and therefore ship noise is basically masked and is not so highlighted as in this other figure here. So it's more or less following the curve of the ambient noise, and that's why we kind of conclude that ship noise is not contributing so much during the open water season. Let's see if I can go to the next slide. So now this is just better seals. So I'm moving to marine mammals, basically. So the same story. We have the better seal contribution in the ice season on the left side and on the open water season on the right side. And you have the three blue curves corresponding to the 25th, 15th, and 75th percentile of background noise during the ice season, or 25, 50, and 75th background noise in the open water season. So you can see again how the better seal sounds have this bump here between 250 hertz up to maybe 3 kilohertz. So that's the amount of energy they're putting into the environment. That is quite different from the curves of the ambient noise. So better seal is an important contributor during the ice season, but it's not so much during the open season. So even if they are present in the open water season, the recordings show that the sounds were faint, and they're faint enough to show that all the files where better seals were detected have a 50th percentile that is basically matching the 50th percentiles of the background noise, which means that they were too faint to really show any difference in that spectra. Basically, there is very little or no contribution by these species during the open water season. So that's how we can compare the different contributors to the background noise and characterize who is the most prominent or the most important contributor in each of these locations by different seasons. We can also compare different contributors without considering the background noise. And so this next slide is showing you basically the main contributors, the main species for WT1. So basically you have the median curves computed, basically it's the median values for each independent source. So you have a comparison that is showing the vessel noise, which is the red line, and the bowhead whale, bird seal, and walruses for ice and summer. So you can see that vessel is basically overlapping and exceeding the levels for all the other species. So it's louder than all the other species. It's masking those signals when vessel is happening in the background of bowhead calls or very slow calls. On the other hand, in the upper water season, you see that ship noise is not so loud. It's only masking the walrus signal. You see the walrus, the green line on the right panel is way lower than the red line for vessel. So in this case, we can see that vessel is not really generating such an effect in these other species. It's only waters which might be affected by that sound. And the spectra is more or less following the acoustic energy for both bowhead and berry seals in that open season. So we can compare those different contributors, not just with ambient noise, but also between them to figure out who is more dominant than other. And just another example of how we can use this particular method. So basically what we, as a conclusion, basically is that this methodological approach allows describing the acoustic contributors of different sources and species to the environment, considering the differences in the background noise by season and location. And that's kind of a hard one to understand, but basically we have a very variable by nature, very variable noise generated by the environment. And so we need to use that variability to be able to compare it with the different contributors. And that's, the way we came up to do that is using those percentiles, the 25, 50, and 75 percentiles, and compare them with the different spectra from different sources of sound. So future work, this is something that we need now to continue, complete the analysis across years and locations in a selection of the moorings, because basically we have limited funding. So we picked mooring locations and years with what we think is important, and then we analyze the data in this way. And so basically we could finally end up with some trends over time. So what I just wrote in this slide is showing you what we're planning to do over the next year or two. So basically, we need to explore trends in the acoustic environment across the last decade, and so looking for possible increment in anthropogenic contributors. So basically, vessel noise will be a very important one to look into, but also changes in marine mammal diversity and seasonality. So basically, we know that there is dispersal going on into Arctic waters from subarctic or even not even subarctic species. So with global warming, we could track that dispersal, looking at which contributors are showing up through the years in these moorings. Similarly, we can look at the changes in ice concentration. So that will likely reflect in the acoustic footprint. So less ice will basically make these quieter periods shorter in time, or basically the open water season will be longer. So we have a noisier season expanding in time over the years. And we could look into that variability within different locations. So that's just some ideas of things we want to explore. The data also allows comparing these results with other data sets. So for example, if we are thinking in vessel, if we could use the AIA's statistics of vessel traffic and spatial distribution, then we can look into the acoustic footprint compared to where these vessels are and based on what density of vessels or types of vessels passing through the area. And same with oceanographic information. If we can compare acoustic results with biological or physical oceanographic data collected in these moorings, then we can start looking for correlation between patterns of oceanography and marine mammal presence or changes in the acoustic space for these species. And again, this is always, if we could have more funding, we could definitely expand the way this data can be exploited in many directions. And I wanted to finish with acknowledging for sure the captain and crew of the vessel, the Aquila, that has been really helping Catherine's team along these past years to really maintain this mooring network. And of course, the funding agencies, BOEM and the National Marine Fisheries Office of Science and Technology. Thank you.
Thank you, Manuel. Are there any questions for Manuel?
Just a quick comment. This is Carol Jansen from AUS. Manuel, we're up here in Alaska. We are working on a project with AIS ship tracking data and taking the last 5 years of edited and quality controlled AIS data from the Arctic, so that bearing all the way through the Beaufort Canadian border. And we are creating density maps, heat maps, and you can query the data in a lot of different ways by ship type. We're working on those actual queries right now. So you might be interested in seeing some of the plots that we're doing with those, and I'll send you some links after this workshop sometime this afternoon, and just let you know and make you aware of that. I was with Catherine at a meeting a couple weeks ago, and I didn't think to talk to her about that. Maybe I mentioned it to her, but so I'll make sure she's CC'd on that as well.
Yeah, and I think Catherine is in this call. If she's here, she can probably mention or give you more details, because there's definitely been some effort. We know there is, I believe, Catherine, 2 different groups. One is Audubon Society, which we have been talking to, and I think there's another group that is also interested in looking at the AIS data and basically creating these heat maps of ship density and basically trying to overimpose the acoustic field, the footprint, the acoustic footprint that this vessel density is generating in the Arctic. But Catherine, I wonder if you're here, can you maybe give some more comments?
Yes, can you hear me?
Hi, Catherine.
Yes.
Okay, good. Hi. Yeah, so we did receive a small amount of money from the Office of Science and Technology to compare 3 mooring sites in Unimak Pass near the Bering Strait, and then up on the Chukchi Plateau. And the analysts right now are going through to get the species presence and vessel noise and all that, and then we will give those files to Manolo to do this very thing. And the thought there is it's 2 places with a lot of vessel traffic versus one that should be pretty pristine. So we're excited to be able to compare between moorings like that.
So are you working with someone who's doing AIS data analysis?
Yeah, so we're partnered with Alaska Audubon. Ben Solander, I believe is how you pronounce his last name, just on those sites.
Great. I'll send you the information that we're doing. Part of our effort is to get data in a format that's consistent across the board. So this is a big data project. This is, for the entire Arctic, but actually our data team is working on the national AIS data sets right now for NOAA. And
that would be great to be able to.
So, yeah, so this is something that you guys are going to definitely be interested in seeing what we're doing, because it is focused right in the area you're working in. So I'm going to get you tied into that project and and some of the tools we're developing for that, so that you'll have access to that.
Perfect, thank you.
And you can give us some feedback as well, because we're right in the process of, developing those tools.
That'll be great.
That's great, thank you. And so I think it's not just the interest. I think is not just in looking at the spatial and temporal distribution and how the vessel density is affecting the soundscape. I think there is the recent studies looking into this in other regions are finding out that is very specific types of vessels, or the combination of different vessels, who are really making a big difference in the soundscape. So I assume that the AIS data you are processing includes the type of vessel or some information about the vessels.
Yeah, you can query the data by vessel type or a multiple vessel types, or look at all vessels together, and that's some of the information we're interested in getting. So like we've broken it down by tankers. You can do it by vessel size and things like that. So yeah, I'm going to send you some links today so you can kind of see where it's
that definitely sounds really interesting.
I think you'll like it, because we've only gone back. I mean, the AIS data for the Arctic is not it doesn't go back as long as your moorings, probably. The other thing I wanted to mention, and just really quickly, is that we have all the shell acoustic data, and we're trying to find a way to get it backed up. So at some point I might want to talk to you guys about, that, and, whether or not what its value is to you guys. Kate Stafford's aware of it. And
how long are those time series, Catherine?
JASCO has been out since 2007, and the good news with their data set is that they began using ARLs just like we did, so it'll be easy to compare their moorings to ours as far as noise goes, because it's the same instrument.
Yeah, so I think it's about 10 years of data. I don't know exact locations of the stations, but or if that overlapped your map that you showed, Manuel. If it showed the Shell stations, but probably not, because the Shell data was not public at that time. So we're trying to find some funding to get it off of hard drives and onto a secure system, and then we'd be in the process of how do we make that data available to people? So if we start getting some success with financing that endeavor, then we will be calling on you to help us deal with that big data project.
So
Yeah.
to answer your question, Carol, the gray dots there do include the JASCO moorings, because I had those positions from Dave from a long time ago.
Okay, but you don't have the data, is that correct?
So we do not have the data, no.
Right, okay, good. All right, so just the gray ones include those plus other industry stations.
Right. It's Green Ridges,
right,
JASCO's, Kate's, Scripps, and Cornell, and there's some in there from Japan as well.
Do you have the Hill Core data? Because they've been doing acoustic sound work in the Eastern Beaufort off of Endicott for, or West Dock, I don't know for how many years, but a lot. And I'm hearing grumblings from them that they don't think anyone's using those data. So are you aware of those?
Who's actually collecting those?
Well, it was required under their EIS or their NEPA agreement to do sound, ambient sound. And it's currently, those oil fields are now being managed by Hill Corp.
Is it the stuff out by North Star?
Prudhoe Bay area, yeah.
So those are the Susanna Blackwell from Green Ridge ones, and I believe those are on there.
And also, I think Hillcop is also doing some work with BioWaves. I think they did that for, if that's the same project. I think there's a cable laying operation and also seismic surveys somewhere in the Beaufort Sea where I think they should contract somebody to do the stuff. I think it's BioWaves who did that. But yeah, so in a way, I mean, those data sets, Carl, I think are really interesting. I think the main difference, I would say, from most of the industry recordings is they are happening when there's a disturbance going on. So it's not like the baseline that we are collecting with Catherine's network. So it's really useful because it can help us somehow get more resolution in space and also in the duration of those events, because we have recordings next to those disturbances. But I think that many of those are only seasonal, where they deploy them just before they start and just after they finish the activity, and few are staying before or after, which I think is really important for this type of approach where we're trying to understand the baseline in the Arctic. But I think, again, the idea of putting this map up in the presentation was to show that there's plenty of data that has been collected over the years that was just only used for one specific task, to do a sound speed verification or sound source verification, or just getting a sense of mammal presence, but wasn't really used for this broader scale, more kind of an ecological approach of, how the soundscape is being generated in this area and how is it changing through time.
Manuel.
I think the shell data actually was out there before they did anything. So that's probably got some good background. And I'll find out from Hillcorp how long their time series has been going on. But yes, that would have been installed after the Endicott causeways were built in the 80s.
Sorry to interrupt this conversation, but we have two early career science.
I have one more question. One quick question, Meredith, please. Okay. Manuel or Catherine, do you have a sense of how much work has been done along these lines in other countries in the Atlantic sector or Canada?
Catherine, do you want to go ahead?
No, go ahead. You know more about Europe.
Well, I think this is a very, very new field, and so there is some. Cornell, the BRP, the group has done quite a bit of work in the Staaterman Sanctuary near Cape Cod, and there is some focal spots where there's been an intense work done because that's where the funding went in. But in general, at least in Europe right now, what's going on is through there's a marine directive, a new marine directive that is forcing all the member states, all the European countries to monitor ambient noise in a very specific way with specific protocols. So they are starting to implement listening stations and networks to really get the information needed for complying with this new law. But it's just they are at the very beginning. In other regions, I think, in the US, I would say the Staaterman National Sanctuary is probably the most advanced place where they have been looking at soundscape analysis over the years, and not just for right whale and ship noise issues, but also in general, and looking at for invertebrates. But I don't know if there is any other major group or location, and I think it's a very new field that is just starting.